Hello, AP. We are going to talk about tonight's little lesson, which hopefully won't be too long, is called empirical formula. Okay, now the definition of an empirical formula is what's listed there. It's the simplest ratio that you can have for subscripts in a formula. Okay, so it's the lowest value for the subscript and the simplest ratio between two atoms. We can go back to when we wrote formulas and we were crisscrossing. I always have you ask the question before you just routinely crisscross whether or not the two charges that you've written in the binary compound or with the polyatomic ion and a metal, whether they add up to 0. Because if they add up to 0, I say just rewrite it neatly without the charges. If you routinely crisscross without thinking about it, you could get subscripts that are multiples. Again, be very careful with oxalate. What's the other? There's a couple other ions, but oxalate C2O4, you don't ever want to reduce that because that itself is the ion's formula. But when we do the crisscross to get our final, you want, for empirical formulas, okay, so you have to understand this is where it gets a little bit confusing, because we'll start to talk about molecular formulas in relationship to empirical formulas. A molecular formula is how something exists in nature. So if it is molecular and it is covalent and it is shearing, it can have a multiple subscript in nature. And its empirical would be the reduction of that to the simplest form. Ionic will always be empirical. Okay, ionic is always empirical. So let's do this. I'm going to move this up just a little bit. And up at the top, you can see there's the molecule, that's sugar, okay? And if you reduce it to its empirical, it actually looks like an aldehyde formula, but it's not. It's just the empirical of the sugar. So it exists in nature as C6H12O6, but its empirical formula is CH2O. That's the difference. Molecular is how it actually exists in nature. Empirical is its simplest form in ratio of mass, of how many C's, how many carbons, how many hydrogens, and how many oxygens. What would be the molar ratio of those if you look at mass-wise? Again, when we look at empirical formulas, ionics will always be empirical. I'm just trying to get it so that if I go and write on it now in my little full screen snip, I have what I need. So here's the important thing. Ionics are always empirical. What does that mean? They always have the lowest ratio subscript. However, molecular formulas can be both empirical and molecular, or they can be just molecular and then you have to reduce it to get its empirical. NH3, empirical and molecular. Simplest form. H2O, empirical and molecular. Okay, but H2O2 is just molecular. If you were to reduce that, it would literally just be HO. Okay, so that would be the empirical. Just keep in mind, when you get to molecular substances, you can have this duality going on. So how do we calculate these? Often you will be given data and asked to find the empirical formula. So when we go to do our moles quiz, empirical formula composition will be on it. You'll have to know how to do these steps. This can get confusing because we learned weighted average, and in weighted average it's a similar thing. You're working with percentages, but in weighted average you just take the percentage and you turn it to a decimal, and then you do your multiplication and add. This is different, so keep straight the difference between weighted average and percent composition. because you have to know how to do both. So just make a little mental note that this can be confusing, so you better make sure you can compartmentalize the two different calculations in your brain, and you can readily recall how to do the two different calculations in your brain. So when we do a percent composition, you're given percentages of each element that is involved in the composition of the material. And we go exactly by these steps. Right? You have to have the steps memorized. So, like over here, it says memorize these steps. Okay, that is not an understatement. That is a word to the wise. Memorize those. Right? Don't think, oh, I don't have to worry about it. No, yeah, you should. Right? I'm going to blow this up a little bit more and move it over and then move up and down so you can really see it and you can see what I'm writing. So we will get to combustion analysis in a minute. I'm going to show you combustion analysis. I have to take an evaluation of how much time we have. AP no longer has you do actual true combustion analysis. But you need to know like why it's valid and how you can manipulate data. And I don't mean like manipulate it to make it fraudulent. I mean like how to just calculate stuff with it. So let's go first through the percent composition. In percent composition, you're going to write your percentage as grams. So any percent you're given, if you're given 12% carbon, it just gets changed to 12 grams carbon. Okay, so just literally like if I get 12.0% in the value, you just say, oh, it's 12.0 grams. Okay? So you just change your percentage to grams. You go to the periodic table and you're going to divide that number of grams by the weight of the element that they're talking about. So you get moles, and that's why grams go to moles. Grams, and then really you're converting to moles, right? That's a lousy arrow. It's hard for me to write on this angle. I still haven't gotten the knack of it. You're converting to moles. Now you look at how many moles you have of each, and then you're going to divide by the smallest number of moles. And then that's where you round. Okay, you round after this step. This is like after you divide here, after number 3 step, then round. Don't round before then. A lot of people round on number 2 step and that throws you off. Don't round. Okay, make sure you keep definitely your number of significant figures minimally. You know, like I say, don't round to the very end. If you have to carry a few more decimal places so that you have some meaning, carry them. Right? Don't round until you're done with number 3. After you're done with number 3, those numbers become subscripts, except if you have a decimal place that isn't close enough to round. In other words, if your decimal place is 0.5 something, this is in the middle. Well, how do we know? What, do we round up? Do we round down? How do we know? So in that case, you would take every single result for number 3 and multiply it by 2. Because that would take everything in proportion and take your half and make it a whole. If it's 0.33, you multiply by 3 because it gets you close enough because you'll be at 0.99. We can call that and round it up the number. The ones that you can round are 0.1 and 0.9. Other than that, I give you 0.9 something or 0.1 something as long as it's not 0.17 because that's really 0.2. You can round 0.1 down, you can round 0.9 up. Other than that, you've got to use the multiplication factor on every result. So this is, you're going to do this on every result for 3. Step number 3. Some people just do it on one thing, and that's not keeping everything in proportion. Okay, so here's an example. I'm given the following percentage: 40.92% carbon, 4.58% hydrogen, 54.50% oxygen. What's its empirical formula? Well, first step, just take the percentage and make it grams. So see, all I did was take this and say, okay, now it's a gram. Now all that percentage has become a gram. I go to the periodic table. This is off the PT down here. These are all off the PT. And yes, with hydrogen, I kept it at 2 decimal places because that's all AP wants. If you're thinking, like for instance, let's say they gave the percentage all the way to the hundredths, you might say, you know what, I'm going to take the weight of hydrogen to the hundredths to keep 4 sig figs. But if you notice below, I still kept 4 sig figs. I didn't round yet. So I divide and find that number. Now remember, I keep these. Don't round here. No rounding. You know, and I should really specify that. Don't carry out 12 decimal places, but don't round it to a whole number. You lose your information. Now you take the smallest value. So this is my smallest value, and I divide every value by that. So if I divide everybody by that, this is the result I get. This one right here. And when I look across, I go, oh crap, I got this baby right here that I can't round. It's somewhere in that middle, and because it's a 0.33, I'd have to multiply everything, and notice in step number 5, everything is multiplied by 3 to get it to be the empirical formula. So if I do this, now these are the subscripts of those individual atoms I've calculated. And that's why if you go back up here, this is the result. Okay? That's empirical formula. If at this step right here, everything was a whole number, you're done. Because this is step 4. I didn't put that in, but this is step 4 here. This is number 4. Well, actually, you're attaining number 4 here. That's your whole numbers. And then you go through and you go, oh crap, and you have to do step number 5. Okay, so that is empirical formula. Ooh, I didn't open up a worksheet. So let's open up one so I can show you. Hold on as I open this up. I just have to find the right one. More math, it's got to be this one. Hydro's number, mixed mole problems, we're getting there. Nope, we're coming. Percent composition of hydrates, empirical formula, right here. Here's one. So this is out of your work packet. So if you open your work packet up to page 11, if we look at going through the steps, I have 75% carbon, 25% hydrogen. So I change that percentage, and I'm going to change my color pen just so it's a little darker. Okay, so I'm just going to change that to grams. Take my hydrogen, change it to grams. Okay? So that's step 1. Step 2 is to go to the periodic table and now divide it by its formula weight. Okay, so I'm going to do that division and I'm going to get a result. So, oh, whoops. Yeah, I hit the wrong button. Nope, can't be that. So I get 6.245. And you might say, well, you only need, there's only 2 sig figs there. Now remember, we'll look at that later. We're going to carry decimal places. So I have 24.75. Can't read my calculator. I look at these numbers here and I find out which one's the smallest. So this is the smallest. So I divide both of those by the smallest number. Well, of course, this one's going to equal 1. And this one equals 3.96, which we're going to call 4. Right, so my subscript for carbon is 1, my subscript for hydrogen is 4. I don't have to write the 1. So my empirical formula is CH4. Okay, just things to remember. If these guys right here were not close enough to be called and rounded up, you would have to multiply by a factor. Okay, so that is empirical formula. The only thing I'm going to go back to is the relationship between empirical formula and molecular formula. So depending on how far we get in class, molecular formula, again, is because of things that are covalent. They will be molecules. Please, please get that straight in your head. They will often flip back and forth between calling it covalent and calling it molecular. So you have to understand that these two things are synonymous. And remember, it is the actual ratio that exists in nature. So once you find and know the empirical formula, if they give you a mass for the molecular mass, how it exists in nature, you can easily find the molecular formula. It's a ratio, right? So I say, how many goes into? That's what I always ask you. How many goes into? How many empirical formula masses goes into that molecular mass? So again, there's steps, right? It's pretty intuitive once you do it enough, but you have to do it the right way. So once you have that empirical formula, so you need the empirical formula in order to do this. There is another way to do it, and I can show you that way on a couple of the worksheets, but I will tell you this is the easiest way other than adding another way to calculate it. So you start with the empirical, you find the empirical, and then you take the molecular mass and you divide it by the empirical weight. So you have to find what I call the empirical mass of the compound, and this is of the empirical formula. You either calculate it, a lot of times it's a two-step project, all lumped into one, because you do the empirical formula first and then you do the molecular. So once you have this, by adding up all the formula weights, just like you normally would, you're going to take that mass and divide it into the mass that's given for the molecular mass. So here's an example off to the right. It says the molecular mass of the compound with empirical formula CH2 is 28. So here's my empirical formula. This is the molecular mass, the real mass, how it exists in nature. So if I know how much this weighs, I can figure how many of these are in that mass. So I go ahead and add up like I would to get a formula weight. I have 12.01 from the carbon and 2 times 1.01 from the hydrogen. So this is how much empirical weighs, and then I take and always put the molecular mass on top. Always put molecular mass on top. Right, so now you divide this into that. Right, when you do that, this number should always be greater than 1. If you're doing it correctly, it should be 1 or greater. Shouldn't be, you can have 0.999 or 0.98, but it shouldn't be 0.5. Then you flip them. Okay? So now that I know there's 2 of these empiricals in a molecular, I take the 2 and I distribute it over the formula and I get the molecular mass, or the molecular formula. Okay, so let me see if I have that open again. Here's my blank worksheets. Let's look at number 1 on this next one. I have an empirical formula of NO2 and its molecular mass is 92. So I have 1N, which is 14.0201, and 2 oxygens, so that's equal to 2 times 16, which is 32. I add them up. I have 46.01. and I have 92, so I take the 92 grams, I divided it by the 46.01, which is about equal to 2. It's going to be a little bit less than 2, just a little bit though, because you have the 0.01 there. And that's because the reason why it's the 92 is because this is a Regents worksheet and they use whole numbers. This is turned out to be 1.9996, which is 2. We're going to round it. So if that's 2, then I take the 2 and I multiply it by the NO2 and distribute this through to the subscripts. So I have N2O4. Okay. Notice this right here. This is a combination problem, because you have the percentages given and the molecular mass, and they want the molecular formula, so you're going to have to find empirical first. There is another way to do it, but I'm not going to show you that right now. I want you to practice the empirical when we get to this stage so that you have it done and it's down and it's in your head. Okay, so that is it for our short lesson. I will hold off on combustion